You're now back for basically the part of the program that's focused very much on an introduction to SNARKs and the languages that you can use and the tools that you can use to build SNARKs. So the first person that I want to introduce to the stage is Alessandro Chiesa, who's going to be helping us understand how to make SNARKs. So let's have Ale join. Hey, Ale.
Hey, hi, everyone. Can you hear me?
Sounds good.
Wonderful. Okay, so I'll get started. Thank you, Anna. So in this talk, titled How to Make SNARKs, I'll provide some high-level introduction to what are SNARKs and what are the high-level paradigms that we use to construct SNARKs. This will lead into the follow-up talks that will delve deeper into some of these paradigms. So some of you may come to SNARKs with the opinion or expectation that they work because of magic, or they involve a lot of moon math, or maybe they're just complicated creatures that they work but they're hard to understand. But the reality is that SNARKs are designed according to rather simple and clear design principles, and they're assembled by using simpler ingredients that are sort of easier to understand. And so in this talk, I will try to convince you that actually designing SNARKs is actually not that hard once you understand sort of the main recipes for them. Okay, so let's get started. So many of you are familiar with SNARKs. Nonetheless, the way I like to think about them at high level is that they are cryptographic proofs for computation integrity. Okay, so the correctness of computations that are super short and sometimes super fast to verify. From a technical perspective, they have their origins in the 1990s, and they sit at the intersection of two areas in computer science. One is computational complexity, specifically probabilistic proofs, and the other one is cryptography, and specifically the area of efficient arguments. So that's what SNARKs are. And in the last 10 years, there's been extraordinary progress in the cryptographic foundations of SNARKs, efficient constructions, and of course, implementations. That's why we're all here, and applications, as many of the companies that you've seen in the sort of sponsor segment of today are working on. And the context is, of course, that while maybe until a few years ago, we understood peer-to-peer protocols like blockchains that's primarily founded on consensus protocols, increasingly, the ability for a node to post to the blockchain a ZK SNARK asserting to some private computation, possibly an expensive computation conducted offline, has become truly another pillar of modern blockchains. And in the many ways that I won't get into, like layer 2 protocols, private computation, that really show up everywhere. And they're really becoming more and more fundamental to this space. So let's dig a little bit deeper. So SNARK stands for the acronym Succinct Non-Interactive Arguments. Okay, so you have a prover and the verifier, and the prover wishes to convince the verifier of some computational statement that it knows a secret witness W, such that some computation F, okay, applied to some public input X, known as the instance, and the private input W, known as the witness, accepts. Okay. And the key property is that the proving process is, say, efficient relative to this computation. So if it takes time t to conduct a computation, you want this to be polynomial or ideally linear in t. This will generate a certificate of correctness that is much smaller. So logarithmic is exponentially smaller, so polynomial in the logarithm of t. And the verification is either OK for the application to be linear, or you want this one also to be super fast. And of course, you cannot just literally depend on log t. You're going to have to read at least the function description and the instance. And so you have to pay for that as well. And this proof can then be published online and be verified by many parties. That's why sort of SNARK that goes on the blockchain, the prover has to work once, and then anybody can check the proof any number of times. Okay, and that's like a cheap operation. Now, many people ask me, so what is a SNARK then? Well, SNARK denotes SNARK of knowledge. That's a technical requirement that denotes some specific property of the verification procedure. I won't get into it right now. And the ZK in front denotes the zero-knowledge property, namely that the proof hides the witness W. And of course, a ZK SNARK is when you combine both of these things. Now, all SNARKs have a trusted setup. It's actually impossible to construct SNARKs without a trusted setup. But there are trusted setups of different types. The most convenient is something that is known as a uniform reference string, sometimes known as a public or transparent setup. It just basically consists of public randomness, okay? So just some public randomness, we agree that it is random, or we know that it is random, and based on that, the prover and verifier can generate and validate proofs. Sometimes, however, you have somewhat more complicated types of setup. These are known as structured reference strings, also known as private setups. And here you have some trusted party that, together with some randomness and possibly some information about the statements you want to prove, for example, an upper bound on the computations you want to prove, it will generate the reference string, okay? And in the real world, there's actually not going to be a trusted party, but it's going to be a multi-party computation, some cryptographic ceremony that simulates this sampling procedure securely. Sometimes you have specific setups where you actually need to bake into the setup the specific function that you want to prove things about, okay? And so this is just to remind you that all SNARKs have setups where they may have different types of setups. This is the most desirable. Why do we even talk about the less desirable ones? Because, well, it's easier to construct SNARKs with these types of setups, and sometimes it is worth to incur the inconvenience of the setup in exchange for other advantages of the SNARK, for example, like a very, very short proof, okay? Like the shortest SNARK proofs known today are known in this sort of, let's say, most inconvenient model. Okay, so that is a SNARK. Where does succinctness come from? Well, it comes actually from computational complexity, this area known as probabilistic proofs. And it's basically, what are probabilistic proofs? It's a variety of different models, all information theoretic, that differ in what kinds of powers and capabilities we grant to the verifier. So here are the types of capabilities that are typically considered. One is you could call oracle access, namely the verifier has the capability to query any location of the prover's messages without actually receiving the entire message. Another one is randomness, okay? The verifier is probabilistic. Yet another capability of a verifier could be interaction, namely the prover and verifier are exchanging messages during some conversation, at the end of which the verifier may accept or reject. Yet another one is having the verifier may have access to multiple provers that are physically isolated, they cannot talk to one another. And depending upon which of these powers you grant to the verifier, you're going to obtain different types of probabilistic proofs. Perhaps the most common, the most familiar of all is interactive proofs that consider verifiers that can talk to the prover and use randomness. Okay, this is the IP class of interactive proofs. Yet another is PCP, probabilistically checkable proofs. So here there is no interaction, there is randomness, but the prover sends a proof that the verifier can then later query at specific locations without having to pay for reading the entire proof, because it's not interested in reading the entire proof. Another class that simultaneously generalizes interactive proofs and PCPs is interactive oracle proofs, okay? We'll get to these later on today. There's also MIP, which considers multiple provers, interaction, and randomness. And of course, you can consider all resources for a class that hasn't really been studied much for MIOP. So why am I putting down this diagram? First, I wanted to at least communicate at a very high level how do different probabilistic proof models differ. It's really all about what powers does the verifier have in this information theoretic model. And I would also like to mention that, especially on the oracle axis, there's a number of different flavors you could consider. The simplest is that you can query a location of the proof, but also people have studied more rich, let's say, query access interfaces. For example, you may request a polynomial evaluation of the proof, or a linear combination of the proof with some tensor vector, or just any arbitrary linear combination with the proof. Okay, so all of these have been studied and they give different types of PCPs. We'll come back to this later. I won't get too much into sort of all of these. I'll just qualitatively say that interactive proofs, the role that they play inside the SNARK world is primarily as subroutines, because on their own, they're actually not that powerful, but the subroutines, they're extremely useful. For example, SumCheck protocol is an interactive proof. So they're mostly used as subroutines of other things, okay? Still, you should, if you want to understand SNARKs, it's something you should be familiar with. PCPs are, for the most part, pedagogically extremely useful, but they are, as of today, very inefficient, and so we don't really use them in practice. MIPs and their generalizations to MIOPs have very attractive features, for example, space efficiency, but they're actually hard to use. We don't really have good compilers to turn these into SNARKs. I'll get into compilers later. I'll just say that I would love to see practical applications of MIPs or more powerful compilers to use them. Today, they have rather limited applicability. The type of interactive proof that is mostly used today in practice is IOPs. Okay, today they underlie most efficient SNARKs. There are some exceptions, but they really show up like in very many places. So this is a bird's eye overview of probabilistic proofs. I'll briefly mention in more detail what is a PCP, because it will be useful later in the talk by Nick. So we said that it is where the verifier is probabilistic and has oracle access to just one prover message. So it looks like this. The prover wants to prove some computational statement. For that, it outputs a very long proof. But the verifier can query this long proof at a small number of locations, as little as a constant number of locations, gets back the answer and decides whether to accept or reject. Okay. Now, crucially, notice that this is not a succinct argument. Even though the verifier is sending a small number of requests to read the proof and get back a small number of answers, you cannot trust the prover to give you the answers based on the queries. You have to first fix the proof and then query the proof after it has been fixed. You cannot. Otherwise, if the prover sees the queries, then it can dream up some answers that will always make the verifier accept. Okay, so this is not something you can conduct basically as a succinct proof. Okay. So as I mentioned, PCPs are rather inefficient. We have amazing asymptotic results that are, however, the constants involved are amazingly huge and they're not really relevant in the real world. There's been a direct attack on PCPs to try to make them concretely efficient. This has led to turning them from galactic algorithms to merely expensive algorithms, but still the proofs involved for the resulting SNARKs are still pretty large. And to this day, there hasn't really been much of a progress on the concrete efficiency of PCPs. So today they remain concretely more efficient and also asymptotically suboptimal. For example, we do not have linear size PCPs. And that's pretty annoying because PCPs are actually really versatile. You can use them in a number of SNARK constructions, but they're quite inefficient. A notable exception that has been used in practice is a relaxation of PCPs, which is known as linear PCPs. I alluded at this earlier. It is a PCP where the verifier is allowed to make linear queries to the proof. These are actually efficient. This is one exception in this area. All right, so what has happened is that people have studied the multi-round generalization, IOPs, interactive oracle proofs, where the verifier can simultaneously leverage randomness, interaction, and oracle access. Okay. And so they look like this. Again, the prover wants to demonstrate some computational statement. And rather than sending just one long proof, it engages with the verifier in some interaction of some number of rounds where it sends a bunch of long proofs, at the end of which the verifier can query some number of locations from these long proofs, get back the answers, and decide whether to accept or reject. The exciting thing that has happened over the past few years is that there's been tons of research in IOPs, and it discovered that we know how to do a lot of much more efficient things with IOPs that we did not know how to do with PCPs. So the interaction really helped. There's many new techniques that have been used to achieve these strong efficiency properties. And overall, sort of 5 years, 6 years later, after IOPs have been introduced, is that we know that we have much, much better efficiency, both asymptotically and concretely. I won't say more about IOPs. I'll just say that probabilistic proofs is a really beautiful but also technical area. It requires understanding coding theory, algebra, and computational complexity. But fortunately, there is good resources out there. There's an online course. You can go to this link to learn about probabilistic proofs. And there's also a summer school that I co-organized this past summer. And there's like a bunch of problem sets that you can use to sort of learn the material in addition to the videos. Great. Okay, so I'll just conclude with a couple of slides to mention how do you go from probabilistic proofs to SNARKs, and that is cryptography. Okay, so all SNARK recipes out there, or almost all, combine cryptography with some type of probabilistic proof, and the subsequent talks will dig into some of these. Some of the earliest practical ways of doing that was a linear PCP together with a linear encoding. More recently, people have studied combining theoretically PCPs, of course, but practically IOPs with something called vector commitments, or sort of hash functions. And also a relaxation of IOPs and PCPs known as polynomial PCPs and IOPs that combine it with polynomial commitments. The key point of all of these recipes is that the probabilistic proof is the one that determines the type of computation you support, whether it's circuits or machine or whatnot. And the cryptography is the thing that determines the cryptographic costs in prover time and in verifier time, whether the construction in the end is pre-quantum or post-quantum, and what kind of setup do you have, whether it's transparent, private, or it is specific or universal. So it comes from the cryptography. You preserve primarily the time and space efficiency of the SNARK comes from the time and space efficiency of the underlying ingredients. And we can instantiate these ingredients using all kinds of different types of cryptography. And you will learn more about this type of recipe in Nick's talk and this type of recipe from Pertush's talk. A notable crossover that doesn't have a clear split is actually something called cryptographic sum checks that, for example, bulletproofs and follow-up work have studied. It's actually some very curious exception to this state of affairs. All right, I just have a couple of more minutes that that I would like to use to conclude. So in SNARKs, not only we are interested in small proofs, but sometimes we're interested in fast verification. And how fast verification is achieved in a SNARK depends on the type of computation that you're checking. So for example, if you're trying to check some machine computation where you have some kind of small description of an algorithm that is computing for a long time, this is usually done by having a SNARK where the verifier doesn't actually unroll the computation in its head, but somehow talks about the description of the computation directly. And kind of, you can think about it, it arithmetizes the computation directly without unrolling it into a circuit. Okay, and thanks to that, it sort of doesn't have to pay for the size of computation T. Okay. Many SNARKs, however, are based on circuit computations, where kind of the description of the computation is the size of the computation itself. So how can you have a sublinear verification in this case? In these cases, you have a situation where you pre-process the circuit and you generate a verification key that is short that depends on the circuit. And in that case, this is how you achieve sublinear verification. This is just at high level. Pertush will talk a little bit more about this. The main point I want you to take away from this is that these are two incomparable approaches. You can either achieve sublinear verification for some computations, mostly machine computations, without pre-processing, or you can achieve sublinear verification for all computations, including ones that are sort of random looking, but you must use pre-processing in that case. Okay, and these are the two main paradigms for sublinear verification, and both have actually been deployed in practice. I'll just point out there's a difference between front ends and backends. This will come up in the last talk. The backend is you have some argument system for a low-level language. Usually this is some circuit language or some machine language. And separately, you need to have some high-level language to reduce. You have a reduction from a high-level language to low-level language. And you've seen some of these names in some of the sponsor talks. There are explicit reductions to reduce to circuits, and there are succinct reductions to reduce to machines. Actually, both Circum and Cairo are and Snarky are sort of languages are used in the real world by some of the sponsor companies. You will hear a lot more about this in Alex's talk. So I'm just about done. This was just a high-level overview for what are SNARKs, what are the underlying probabilistic proofs, and what are the main high-level recipes to make them. And in the subsequent talks, they will delve in more detail into some of these topics. Enjoy the rest of the day.
Thank you so much, Ale, for this talk. I also want to ask you, and we've had this question kind of while you're speaking, a lot of people would love to have access to these slides. Would we be able to have them afterwards?
Yeah,
I don't know if you have them saved somewhere. We were going to collect them potentially and share with everyone, because I know that question has come up a few times. Also, if you have a chance, Ale, there have been actually a few questions in the comments, in the public comments. So maybe you can have a peek in there and take a look. I don't know that I think we probably should go on. I don't know if there's any question you want to take offhand, or if we should just, if it's okay if you answer them in the chat. I don't know how you feel about that.
If someone can, maybe if you can point me to, if there is time and you can point me to a question, that would be great.
Let me pull up one. I think I can pull it up on here, actually. Oh yeah. Thanks, Susanna.
Oh, cool.
So you can actually read it here.
All right. So yeah. So the way that SNARKs help with the symmetry is that you have the prover does the computation once, okay, and then you only have to send to the blockchain this one proof that can then be communicated to everyone in the network, and everybody else doesn't have to do the same computation. It's not so much about network bandwidth, because imagine a situation where everybody else redoes the same computation, then you wouldn't have had to send the proof, right? So in some sense, you're paying more bandwidth, but because the proof is so small, then it doesn't matter too much, okay? What you're saving other nodes in the network is the computation cost, okay? Now, there are other situations where you're proving a statement about data that you don't see, and in that case, you don't have to send that data, okay? So that happens as well, okay? But maybe the most obvious way in which they help is they save computation to everybody else. Thank you for the question. How viable are interactive proofs? So maybe the question is about SNARKs, because the interactive proofs themselves are interactive, right? So in order to run an interactive proof on a blockchain, you would have to interact with everybody in the network, and that would be not feasible. When you put something on a blockchain, you want the thing to be non-interactive so that the person that made the proof doesn't have to be online to interact with you, right? That's why it's important for the SNARKs to be non-interactive. Now, SNARKs are viable in the sense that they are used on Ethereum today. So there are smart contracts on Ethereum running today where there is a SNARK verifier and it receives proofs. And these proofs are attesting to huge off-chain computations. And because the verification is much smaller and much cheaper than the original computation, then overall you save gas fees compared to the naive running actually all the computation that was done offline, off-chain. Thank you for the question.
Oh, let's do two more, and then we...
Okay, so how do you know you can trust the randomness in a structured setup? It does have to be proven in some way. It's a great question. Well, you don't. That's why it's a trusted setup, right? So in the simplest, even the simplest type of setup, where all you really want is just a random string, you have to kind of use real-world methods to, for example, you could chop the first 1,000 digits of pi and call that your random string. You know, presumably pi wasn't born to break your scheme, right? It's kind of exists long before we designed these schemes, right? You could also have some coin flipping protocol between some number of parties to try to collect with some cryptographic property where, I don't know, some majority, if the majority are honest, then the result of the coin flipping protocol is guaranteed to be random, right? So it is not a simple answer, and all setups in the real world require some care, and the more complicated the setup is, the more complicated it might be to deploy in the real world, with the most extreme situation being you have to run cryptographic ceremonies between large number of parties so that with the security property that if at least one of them is honest, then the setup can be trusted. Okay, but this is unavoidable because all SNARKs need setup. There is just no SNARK without a setup. It's just about the type of setup.
Okay, I'm actually getting the note that we may not have time for another question. I'm so sorry.
Thank you
I
for the
thought we
question.
could sneak 2 in. Thanks so much, Ale. And yeah, there are a few more questions in here, so maybe you can help answer those in the chat.